We're going to take a look at our logistic function and see what adjusting the parameters a, c, and k does to the graph. Now first off, let's take a look at what's happening. All a, c, and k are set to 1. Here's our logistic function. Notice it's concave up. We've got an inflection point at 0, and then it's concave down. It's always increasing. Exactly what we had seen from looking at the derivatives. Now notice there's a horizontal asymptote at 1 and at 0. Watch what happens as we change a. As a increases, our horizontal asymptote increases. For instance, if a is 5, our horizontal asymptote goes up to 5. So a is what we call the limiting value. It's as high as this function will get. Watch what happens as we change c, this parameter right here. As c gets larger, notice our inflection point starts to move to the right. So now our inflection point's over here. So let's move c back to 1 and let's add our inflection point to our graph. And watch what happens to it as c gets larger. So if c is 10, we see our inflection point has increased. Not to 10, but it has increased. Now if we change k, as it gets larger, our inflection point will decrease. As k gets smaller, our inflection point will increase because of what we're doing to the function. If we're changing this k value, as it decreases, we're decreasing the rate that this exponential is decreasing at, which increases the overall value. But notice it didn't change our horizontal asymptote, and our inflection point's right in the middle vertically, hence that value of a over 2. Let's raise this up a little to 5 and zoom out so we can get a little bit better view of what's going on here. We can move our function and we can see both those asymptotes clearly. As we saw with the limit, it goes to 0 and as we go to negative infinity, it goes to a as we go to positive infinity. The inflection point sits right in the middle. So now we can kind of see graphically what happens with these. Often logistic functions are used to model a population that has some sort of limiting value due to their surroundings. Because what happens is that population starts really small, it's going to increase and then increase very quickly for a little while, but then as it gets closer to the constraints of its environment, it increases less and less quickly until it eventually levels off. So it's very useful for modeling populations that are going to have some kind of constraint limiting their growth.